Hi everyone! For my project, I wanted to incorporate my epidemiological background in conjunction with machine learning. This project is intended to understand whether we can more accurately track and predict flu outbreaks using real-time social media data such as Twitter. Currently, we have CDC data, but it's on a 2-week delay, so any updated data is always going to be 2 weeks behind. If we're able to incorporate real-time Twitter data, we might be able to more effectively identify cases as they're happening and even more accurately predict future outbreaks. My project was built with Dash as the front end and Flask as the back end, and the project was broken down into 2 phases. So the first phase involved training machine learning classification models in order to accurately capture all tweets that were actually indicative of someone being sick with the flu. While we can filter tweets by certain keywords such as flu and influenza, I wanted to be sure to only retain tweets that were relevant for my analyses. Now there might be some tweets where users are discussing their flu shots or the flu season. Those aren't actually tweets that I wanted to keep for my analyses. Once I trained a machine learning model to correctly identify relevant tweets, I can then feed those relevant tweets into a time series analysis, and this is the second phase of my project. Comparing a model with just CDC data and a model with CDC and Twitter data to see if the Twitter data actually contributes to the model in some way, such that it predicts more accurately. The supervised learning aspect of this project means that the models actually need to learn from or be trained on a labeled dataset before they can be used for future classification. I took about 4,500 tweets that were actually representative of the dataset and labeled them 0 or 1 or unrelated, related. And an example of a related tweet is, just caught the flu, over here sneezing. An example of an unrelated tweet is, how to avoid getting the flu or cold. And as you can see here, the distribution of the annotated tweets was fairly even across the 2 classes. Now how do we process these tweets? Raw text as it is cannot be fed into the machine learning models. They need to be vectorized. There are 2 approaches, the bag of word approach with count or TF-IDF vectorization or the doc-to-vec approach. The bag of word approach essentially throws all of the known words from the corpus or the collection of tweets into a bag, and each tweet is characterized by the occurrence of the known words. This approach does not consider the context or the order of the words, as opposed to the doc-to-vec approach, which generates vectors for the tweets. N-grams was also used, so unigram to bigram to trigram, or essentially the number of words in sequence that are being considered. So for the unigram approach, only single words are being considered, whereas for the bigram approach, 1 to 2 words in a row are being considered, and the same for the trigram approach, 1 to 3 words in a row are being considered. And validation accuracy was used to assess the best approach. As you can see here, for this particular data set, trigram TF-IDF vectorization was considered the best approach. And it's important to note that the tweets were actually cleaned before processing. So URLs, special characters, numbers, emojis, they were all removed and contractions were changed. So haven't becomes have not, and so on. I also wanted to determine the top 10 most important features or words. So these were actually determined using chi-square tests, which essentially assesses the relationship between the outcome, or labels, and a given word. The higher the score, the more related the word is to the outcome. And you can see here, some of the words are what we would expect, such as vaccine, sick, getting better. I also wanted to see if dimensionality reduction was useful in any way. So dimensionality reduction can actually potentially improve the computation and time required. There might be a certain number of features or words where it's enough to distinguish the 2 classes. The explained variance is enough, and any additional features are not useful. However, you can see here, there is no elbow. The cumulative explained variance continues to linearly increase as more features are added. Similarly, if you arbitrarily reduce the dimensions down to 3, you don't get any meaningful information out of that, and the clusters actually overlap. Once I had determined the best approach to processing my tweets, I could then train different machine learning models on the tweets and determine the best classifier for my tweets. So I trained naive Bayes, logistic regression, random forest, gradient boost, AdaBoost, and SVMs, and used several metrics to assess what was best for my data. So for each classifier, I generated a confusion matrix, which essentially represents true positives, true negatives, false positives, and false negatives. So what are the related tweets that my classifier is actually identifying as related, and so on. The ROC curve essentially plots the true positive rate versus the false positive rate at different thresholds. Ideally, the curve would peak sharply with a high true positive rate and a low false positive rate, and the area under the curve would be higher than 0.5, or chance alone, which is what the dashed line represents. Based on these metrics, I chose logistic regression as my classifier. Now in the background, I had written two scripts which had been running during this entire time. One script was taking files of historical tweet IDs, feeding them into the Twitter API, accounting for the rate limit, and grabbing the associated tweet information. Of all of these tweets, only tweets with certain keywords, such as flu or influenza, were stored in a Postgres database. At the same time, another script was feeding live tweets as they were happening, again only those with certain keywords, and storing them into the same database. Over the span of a week and a half, several million tangentially related tweets from 2016 to 2018 were stored. These tweets were then fed into a trained logistic regression model, and only the tweets that the classifier identified as relevant or indicative of a flu infection were kept and used for time series analysis. This resulted in over 3 million tweets from 2016 to 2018. When these tweets are actually plotted against CDC weekly flu-related visit data, you can see they line up fairly well, and there's a seasonal aspect to the data. It must be noted that last year, or 2017 to 2018 flu season, was particularly bad, but there's definitely a seasonal aspect to the data. The 2016 to 2017 flu season was also noted with a peak in both visits and tweets. Now, the data must also be processed for subsequent analyses. Regression modeling is contingent on several core assumptions, one of which is that the observations are independent of each other and do not influence each other in any way. And this is evidently not true. When you look at the mean and standard deviation, they actually move in time with the data, and we want them flat. And this is corroborated by the Dickey-Fuller test, which confirms that the data is not stationary. And you can also see this when you're looking at the autocorrelation and the partial autocorrelation plots. There's definitely a seasonal aspect to the data. In order to stationarize the data, first seasonal differencing was applied to the data, and stationarity was confirmed with the Dickey-Fuller test. Two seasonal ARIMA models were then constructed, one with just CDC data and one with CDC and Twitter data. One step ahead forecasting was used to validate and compare the models. A given model can make predictions, and those predictions are then compared to known values. And it turns out that the model with both CDC and Twitter data actually does better at forecasting with a lower error rate compared to the model with just CDC data. This has many implications for prospective disease forecasting. With the plethora of data that we now have available to us, we have the opportunity to truly improve population health. I hope to continue to move forward with this project by incorporating more data and experimenting with additional machine learning algorithms. Thank you for your time.